So as noted at the end of the previous video, my first pass at this was way too long. So I've split it in two, and recording a new introduction that's going to give way in just a second to a very abrupt jump into the second half of the original video, which is going to tell you all about how Einstein came up with a theory that explains the photoelectric effect. So in the early 1900s, physicists were sort of casting around trying to figure out a way to understand these anomalous results, right? What is a model that would allow you to explain what's going on here? The answer actually came from Albert Einstein, who was then working in obscurity in a patent office in Switzerland because he'd been unable to get an academic job after completing his PhD. This is a situation that still happens today. So Einstein, working in the patent office, he published a paper presenting what he called a heuristic model of the photoelectric effect, and that just means like here's a way of thinking about the photoelectric effect that would explain what's going on here. And in doing this model, he was picking up on what Max Planck had suggested earlier, this notion of a characteristic energy associated with a frequency of light that you can only emit light in integer multiples of this characteristic energy. Now, Planck applied this to the things that were emitting the light and said that these oscillators could only emit integer multiples. But Einstein said, heuristically, that's the same thing as if the light itself is coming in these characteristic multiples, in integer bundles of energy. So Einstein is really taking Planck's idea and applying it to the light itself, saying the light behaves like a stream of little particles. He called them light quanta, but today we would say photons. That each of these light quanta has one unit of the characteristic energy that Planck identified in his black body model. If you do that, Einstein said, then you can explain all of the features of the photoelectric effect, right, in terms of this model where light behaves like a particle. How does this work? Well, let's think about this one successful prediction. Let's think about the number of electrons per second that come out. Well, that's the one that worked for the wave model, but it also works great for the photon model, right? If you talk about light as a stream of particles, the more intense the light is, the more particles per second must be coming in that beam, which means the more particles you have available to knock loose electrons. So if you increase the intensity, you increase the number of photons in your beam of light, you should also increase the number of electrons that come out in the photoelectric effect. So that works great for the photon model. The photon model also explains all of the things that fail for the wave model, right? If we look at the energy as a function of the frequency, right? High frequencies are photons with a large characteristic energy. They're bringing in a lot of energy. If we just say that there's some amount of energy needed to pop an electron out, a short wavelength, high frequency photon comes in with a lot of extra energy above and beyond that minimum. So when the electron comes out, it just takes all of that energy away. It comes out with a very high energy. If we go to a lower frequency that just barely has enough energy to get the electron out, then the electron comes out moving very slowly. So at lower frequencies, the energy should be lower than at higher frequencies. And this also explains why there's a cutoff frequency. If it takes some minimum amount of energy to knock loose an electron, then there will be frequencies for which the characteristic energy of the photon coming in is just too low. It doesn't have enough energy to knock loose an electron, and so you'll never get any light and any electrons coming out, no matter how much intensity you use. Right? The photons don't have the energy that they would need to knock loose an electron, so you just don't see any at all. This also explains why the number of electrons that you get decreases as you go to higher frequencies at the same intensity. Right? If you go to higher frequencies at the same intensity, the number of photons you need to make that intensity is smaller. So you have fewer photons, fewer high frequency photons in a beam with an intensity of 1 milliwatt per square centimeter than you do low frequency photons in a beam of 1 milliwatt per square centimeter. So the higher the frequency, the lower the number of photons, the lower the current that you should get out. So Einstein's photoelectric effect model, then we can summarize, matches all four of these predictions very nicely. Right? It predicts that the number of electrons you should get out at any frequency for which you get electrons, the number should depend on the intensity. You increase the intensity, you're increasing the number of photons. That means you're increasing the number of electrons that can get knocked out. It explains why the energy of the electrons does not depend on the intensity, because each electron is knocked out by one and only one photon. It doesn't matter how many photons you have. The energy of the electron that comes out is just whatever's left over after the photon gives the electron the minimum energy that it needs to come out. That also explains why there's a cutoff frequency, a minimum frequency below which you don't see any electrons coming out at all. And that's because there's this minimum energy needed. And if the characteristic energy of the light, of the energy of a photon, is too low, it just can't knock any electrons out. And this also explains why the energy increases linearly with frequency above the cutoff, because the energy of the photon increases linearly above the cutoff. This is just taking Planck's idea of a frequency dependent energy. So the energy is equal to the frequency multiplied by some small number. That number is now called Planck's constant. That gives you this linear behavior that tells you that you should see straight lines in a graph of the energy as a function of frequency. So Einstein's model makes very clear, consistent predictions. Those predictions match very well with the experimental data. So of course you would think that everybody immediately latched onto this and thought it was a great success. You would actually be wrong. People hated this. This notion of a particle model of light is just such a radical idea. Taking this, Planck's idea was an ugly trick already. Taking it and applying it to the light, which everyone knew is a wave, right? Saying that the light is actually behaving like a stream of particles. That was just a bridge too far for most of the physics community. My favorite illustration of this is this actually comes from a recommendation letter that Planck wrote for Einstein, recommending him for admission to the Prussian Academy of Sciences. Planck admired Einstein's work on relativity enormously, thought it was great, but really hated this photoelectric effect business. And so in the process of recommending Einstein for a position, for an honor, he wrote that he may sometimes have missed the target in his speculations, as for example in his hypothesis of light quanta, cannot really be held too much against him, for it is not possible to introduce fundamentally new ideas, even in the most exact sciences, without occasionally taking a risk. So this is Planck saying, this guy's really smart, he's got lots of ideas, he's got lots of new ideas that are really exciting. Some of them are just wrong, but don't hold that against him because he went way off base on this photoelectric effect thing. Sorry about that. But the relativity stuff is great. You should totally hire it. That's Planck's recommendation. Okay. The nice thing about this, from the standpoint of Einstein and his theory, is that this is an eminently testable theory, and so people went out and tested the theory. Even people who really hated the theory. So the most famous test of this was done by the American physicist Robert Millikan, who wrote in talking about why he was doing these tests that Einstein's model, in his words, cannot, in my judgment, be looked upon at present as resting upon any sort of a satisfactory theoretical foundation. Those are kind of fighting words in the physics community. That's saying, like, I think your ideas are a bunch of crap. I think you just made this thing up. And the really beautiful thing about this is Millikan wrote this in the introduction of a paper, and in the very next paragraph, he continues that this model represents very accurately the behavior of all the substances with which I have worked. So Millikan did fantastically good experiments on the photoelectric effect and found that when he accounted for all of the factors that make it a kind of tricky experiment to do, took all of the data, he found that his results agreed perfectly with the predictions of Einstein's model. This is an interesting story, not just because this is one of the great passive-aggressive academic writing examples that you'll find in the history of physics. This is also a really nice example because it speaks to the integrity of the scientific process, right? Millikan is a guy who thought that Einstein's model was terrible. He thought that there's no satisfactory theoretical foundation for it. There's no reason to believe that light behaves like a particle. But when he went and did the experiment, he found that this confirmed Einstein's predictions. And he published that result saying flat out, this works. He said, I can't explain why it works, but this works really well. We have to take this idea seriously. Millikan published these experiments in 1916. These papers are from 1916. And that's really the point where people started to take this notion of light behaving like a particle very seriously. The end result is that in 1921, Einstein was awarded the Nobel Prize for his services to theoretical physics. And the one result that they cite specifically is especially for his discovery of the law of the photoelectric effect. Now, there's some stupid politics in this. He's not cited for relativity. Everybody knows that he got it for relativity as well. But there were some people in Sweden who really hated the idea of relativity. And so this is a compromise. Citing the photoelectric effect as a specific result is a compromise that allowed the Nobel Prize people to give Einstein the prize that they all knew he deserved, even though, you know, there was a couple of crotchety old guys who wouldn't stand for him winning it for the theory of relativity. Einstein got his Nobel in 1921. Within a couple of years, Millikan also got a Nobel, in part for his measurements of the photoelectric effect. So, you know, everybody gets some money from the Nobel Foundation. Everybody wins, all is well. So this is a demonstration of why, in the early part of the 1900s, physicists started to take seriously again the notion that light has particle character. This is the photoelectric effect is one of the decisive experiments in this, and it's really important for that reason. This is the launching point for quantum physics. This is the point where people start to think about the really weird stuff that ends up forming the core of quantum mechanics today, about particles, things that we know are waves, having some particle character to them. So this is a really important turning point in the history of physics, and that's why it's part of this class. And hopefully this also serves to demonstrate how evidence changes minds in science, even of people like Millikan, who really hated the theory that they ended up proving correct. So that's the end of this section of the course. So this is, we did a diffraction activity that showed that light behaves like a wave. Now we've done this photoelectric effect, and we see that experimental evidence tells us that light also has to have particle character to it. And that combination of those things, combining those two, is the tension at the heart of quantum mechanics that makes it such a weird theory. The next thing we're going to do is to move to a very different subject. We're going to start talking about how things that we know are particles turn out to have wave character. And to do that, we're going to have to talk about the nature of atoms. But that'll be the subject for the next set of lectures. So, you know, take a deep breath, you know, congratulate yourself for being done with this and having made it through this very long video. And next time we'll be back with something completely different.